Now, as I said, cost sensitive training is something that you can do for logistic regression. Now, when it comes to decision tree or all of its variants, including random forest, standard boost, gradient boost, you can basically play around with this particular feature called class weight, particular hyperparameter called class weight. In class weight, what you're saying is again the same thing. You give a lot more weightage to please class 1, right? My class 1 samples are low, please give a lot more weightage to them. You can manually set what is this class weight should be, and depending on that, so again, there's no right answer to what exactly should be the best class weight. It's a hyperparameter, you would have to tune it, and you have to basically see how your model kind of performs on validation set on each of the possible class weights. So this is what we do here exactly. So we take 50 possible class weights, and we measure, or we basically fit with each of the class weights, we fit a random forest and measure the AUC score and F1 score. And now we see how this looks like. So in this particular case, you can see how this looks like, right? So this is your effect of weight on class imbalance data set. As you can see, for somewhere weight around 15, your model is performing the best, right? So this is the evaluation. You can see that F1 score as well as your AUC scores, right? So this is a AUC score and this is a F1 score. For both of them, there's a peak, very high, sharp, distinct peak around this value, right? So whatever this class weight is, which is 15, is probably the most optimum weight to give to your class 1, right? So am I clear with, I'm hoping I'm clear with the class weight concept to kind of summarize this. So all you're gonna do is you can basically pass this feature, right? Hyperparameter class weight, which is a dictionary which says what is the weight to be given to class 0, what is the weight to be given to class 1. So, and because you can do all of this kind of small variance in random forest, it's also the choice of algorithm that kind of comes into play out here. If you have a imbalanced data set, to use logistic regression, you would want to kind of do cost penalized training, cost sensitive training, or if you're trying to use random forest, you want to kind of play around with this hyperparameter class weight so as to adjust for your class imbalance, right? Hopefully that is clear. So now we are going to talk about some useful tips for your whole imbalanced data problems. So while carrying out cross validation, this is something which I'm really going to stress a lot on. While carrying out your cross validation, if it's an imbalanced data set, it's much better idea that if you kind of do stratified cross validation, right? So the whole idea of doing that is basically making sure that each of your folds that you're validating on has at least the minority class present at least in significant amount, because if you're not doing it, if you're doing it the normal way of random cross validation, where if you know the normal cross validation that you use basically uses random subsamples, right? And if you do that, that's not really a very good idea, because there might be a chance you might lose out on your data, right? You might lose out on your specific folds not having minority class at all. So that's something you want to avoid. The next is obviously instead of predictions, get probabilities. I've probably been telling this you across all the lectures. AUC is the most important, the main reason that I've been kind of voting for, I've been talking about AUC is that it's something which is threshold independent, right? Because if you're directly dealing with prediction probabilities, that's a much easier game rather than if you're trying to deal with predictions classes, right? Class predictions. Because class predictions are based on probabilities and threshold, and that threshold is something that has to be decided by not only you but also after in talks with business and everyone. So that threshold is not something easy to decide. So as long as possible, try and avoid prediction classes and try and work with probabilities. And obviously that kind of follows the fact that you should study the AUC ROC curve and adjust the threshold. So now we are off to other challenges, which are something that we have already mentioned. So we have talked about imbalanced data set. We have talked about how to handle that. I've talked about change the data, which included undersampling, oversampling, change the algorithm, which constituted of cost penalized, cost sensitive training, and using the weight parameter in case of decision tree and all of its variant formats. Now, so the next challenge that we are talking about is dealing with smaller data set. So small data sets basically are problem to train, because these are not talking about it small in one particular class, right? Small data sets are data sets which are overall small in terms of both the classes. There could be class imbalance as well in a small data set, which is a new challenge, But a small data set as a concept is basically where you have very less data points. So what are the things that you can do? In those cases, obviously exploit bootstrapping, which is sampling with replacement, which is basically one idea to kind of the same thing that we did for oversampling, which is basically repeat your data points randomly out of them. The second thing you can do is use simpler regularized method. This is something we have already seen in case of just right now, when we saw that when the data was low, our logistic regression performed much better than random forest, because random forest was overfitting on a very small data. We saw that very clearly in undersampling. Each of those undersampling cases, logistic regression was far better than decision tree random forest, right? So that's the takeaway from that, that always if you have a small data set, always try and use simpler regularized model. That kind of almost always works better. Ensembling techniques, again, be careful. It's not necessary. This is not something that would always work, because ensembling, as we saw in random forest, really did not help us, right? Random forest was an ensemble of decision trees. Even we did ensembling, it really did not improve our performance, because in case of undersampling, that was a smaller data set problem, right? You had 600 data points, you undersampled to 300. Now in that small data set, even you used ensembling, it did not help. So ensembling is something that might not help, so you do not know. So try and see how it goes. There's definitely not a blanket answer that it should always work better. And obviously there's the fourth technique, which is called use support vector machines, which I'm sure you might be going through in the class. If not, go and Google that out. You would be able to learn about support vector machines. Those are more effective techniques to deal with when you have a small data set. So, but apparently at least two things that I'm very sure you have picked up from here is exploit bootstrapping, which is randomly sample points and kind of repeat them. And the second is use simpler regularized models. You have seen both of them in action today. So guys, now we are finally coming to the last part of our data challenge problem, which is what is the optimum value for k, or the value of k in coolness, as you would call it. So what is the optimum value for k in cross-fold validation? So obviously let's first understand why do you kind of need an optimum value. So there's a trade-off, right? If you kind of do your multiple, so we are talking about k-fold cross-validation. In k-fold cross-validation, if you are kind of having a higher k, which means you're kind of splitting the data into a lot more subsets, obviously that's going to result in much higher accuracy model, but that's going to give you a higher computational cost as well. It's going to take a lot of time if you have a lot of splits to kind of check for. Similarly, the same thing kind of applies for lower k. Would probably not have as good a model, but it would be a lower computational time. So given that, there was this particular study which kind of says that up to k of 10 equals to probably a good balance between accuracy and training time. And stratified k-folds obviously seems to perform better. Now, why stratified k-fold performs better? This is something we already talked about in the imbalance problem, because if you have an imbalanced data set and you kind of do a random cross-validation, that probably has a chance that you might have data subfolds basically, which probably would never have a minority class at all. So stratified cross-validation obviously works better than random cross-validation in those particular cases, because you are making sure that your data is amply represented, all the classes, all the particular parts, stratums of the data are aptly represented in the stratified k-fold. Now given that is the case, I would still not like to kind of completely agree with the fact that k equals to 10 is a very good number. This is just an indicative number, thumbs up kind of indicator number. Don't try and stick to this, that probably because it has been written here that k is the 10 is probably a good balance. Doesn't necessarily mean that you should always do 10-fold cross validation. You could definitely do 3-fold, 2-fold, 5-fold, up to you and up to your computational time. This is something you have to take a call. It's fine. You can kind of choose between your what is the best possible metric for you. It could be 3-fold, it could be 5-fold. It's up to you to decide. So for smaller data set, obviously if it comes out to the data set is small, you can have a larger number of k-fold cross validation. You can in fact go to the point where you're actually leaving each one data point out. So that is leave one out, which is the most expensive kind of cross validation. Obviously it goes without saying, the smaller your data set, the higher number of k-fold cross validations you can afford. So that's about the maximum, the value of k in coolness. So there's definitely this takeaway from that is stratified k-fold cross validation works better than random cross validation. But apart from that, k equals to 10 or k equals to 5 is something that you should ideally take a call on based on your computational resource and the size of the data set that you're working on. So now the next part, which is the final part of our challenges in machine learning, is which algorithm to use. Now at the outset of this session, I want to kind of clarify this, that though this kind of gives you some ideas, please don't kind of try and bake this in your head that probably just because Rohit has been talking about this in the session, it necessarily means that this is the best algorithm to go ahead with. I have already talked about it enough in all the lecture sessions across logistic regression, decision tree, random forest, and now today also I explained you what are the cases when logistic regression performs much better than random forest. You have seen it for yourself, so there's no reason for you to believe that there's a blanket answer to the fact that there's an algorithm which performs better than all other algorithms. So it completely depends on the data, if there's a linearity, if there's a non-linearity, if there's data of the size of the data set is small, if the size of the data set is big. So depending, covering all of those features, it's again something that you will be able to determine uniquely for your own use case. For your own use case, there would be an answer to which is the algorithm is better, and that is going to be unique, as that's not going to be something that is generalizable across all data sets. So please keep this in mind. Whatever you see ahead is not generalizable, and it's just an indicator thing to kind of just give you an idea. So there was this paper where someone apparently, well, I would say a lot of free time, did evaluate 179 classifiers, 17 families, 121 data sets, with the sole idea of coming up with this, that if there's a single algorithm, if there's an answer to the fact there's a single algorithm which performs better than all other algorithms. And what are the results that you see here is that the classifiers that are most likely to perform best are random forest, and then there's SVM. Obviously you have not probably been taught about SVM in this lecture series, but that's something you can definitely Google up and see for yourself. Random forest, we have definitely talked about it. It's nothing but an ensemble, bootstrap ensemble of decision trees. Again, note please, just because it says random forest and SVM doesn't mean that for all of your cases random forest and SVM is going to be the best performing algorithm. We have talked about XGB boost, we have talked about boosting techniques. Those are obviously much stronger ways of ensembling than random ensembling, which happens in random forest. So again, these are some things, these are some of the results from the paper. Please don't take it to heart. It's random forest, SVM, that's the order. And then decision tree and AN, and again you probably do not know about two of them already here. Don't worry about them. This is not a blanket list. Please don't follow it strictly. This is the paper summary. So again, the same thing. There's not much around here to talk about. And some practical tips. Yeah, so this is what kind of which is more interesting takeaway from which is the best. So there's obviously, as I've been saying, there's no particular answer that random forest works better than logistic or logistics work better than decision tree. Nothing of that sort. It's something that you have to determine, but there are obviously certain I would say thumb rule to kind of adhere to. So there are two families of algorithms we have talked about: linear and non-linear algorithms. We have started from decision tree all the way to ensembling, so all of them were non-linear models. So the question is when to use which. So as you can see that linear regression methods are something which are very awesome, because couple of things, the training time on large data sets are much small. If you train decision tree, you already know how much computation expensive that is. Now think about random forest, which is an ensemble of multiple decisions. Even though happening in parallel, it is going to take a lot of time, right? So that is the most awesomest thing about it. And also second thing is they are not prone to overfitting, right? Which is probably something that you cannot see out here in the slides, which is basically the fact that linear simple models are very robust to overfitting as compared to say random forest. And again, that's something you had already seen today live in action. You had seen when there was a smaller data set, random forest completely overfit on top of it, while logistic regression did not. So summarizing the whole point in the slide is that if you're starting out your experimentation journey, it's always good to start off with your linear simple models as baseline models, because if those take a lot of less time to do, and also they're not prone to overfitting, right? So which makes them a very ideal case for starting out your baseline. So when you are starting out your machine learning workflow, right, so in starting from all the algorithms, it's always advisable that you start with the most basic thing which forms your baseline, right? Then you kind of try and build on top of it. Then probably say decision tree, then you kind of go a step ahead, random forest, and that's the journey how it should look like. You should never be starting off your journey and you're like, you get the data EDA, you do the EDA, and then you're like, okay, have enough of it, I'm starting with ADA boost. That's not the way you're going to do it in the machine learning journey, because as I've already explained, logistic regressions, simple decision trees, they are very easy to understand, easy to explain people decision tree, right? Decision tree is easy to understand, easy to explain. Linear regression, logistic regression are very much robust to overfitting. So obviously start off with those kind of basic models as your baseline models, and then slowly as you go through and improve your models, right? So this is again the same thing that kind of we have already talked about, the time consuming part of linear regression and logistic regression. The easier methods are much less computationally expensive as compared to the other non-linear methods. And there's obviously this particular thing which I kind of give always an example of, that in case you are, say, working in an ad exchange kind of a thing or a trading kind of a thing where you have to take decisions very quickly, a lot of time you cannot afford doing all of that using non-linear methods, because you don't have that time bandwidth to kind of run a model such computationally expensive. So in those cases you would tend to go ahead with something which is absolutely simple and easy to use. And a lot of times again, interpretability is something that you really care for. A lot of times you really don't care as much about the accuracy as you care about the interpretability. So again, that's something that you get in normal decision tree or simple methods. So finally, summarizing all of that here, you can clearly see for linear regression models, the plus point is the training speed, the prediction speed. Whereas ensemble models are obviously very good if you have that time bandwidth, you are not constrained time-wise, you are not constrained computationally. Ensemble models are obviously much better because they can model much more complex decision. They can give you much higher accuracy. They can basically improve your model performance by a lot, right? So that's a powerful advantage of ensemble methods. And now that's something that you can clearly see. So this is a 2x2 chart, which is easier for you to kind of summarize all of this same discussion out here that we have been having for so long, which is when to use linear versus ensemble or non-linear methods versus linear versus linear or simple methods versus non-simple methods, ensemble methods, right? So that's about it. So that's finally the end of the session for today. So kind of summarizing everything. So we had a look at imbalanced data. So imbalanced data was something where there were multiple classes, and out of them one or more classes basically had a frequency which was much lower than the other classes, right? So you have a lot of less data. So this practical examples are cancer research, fraud detection, sensor data, all of this, and probably a lot more day-to-day examples from your real life if you think about our class imbalance data. Because anytime you're trying to detect an anomaly or rare event, it's a class imbalance, because anomalies and rare events are not occurring every day, right? Earthquake data, anything that you see, anything that you're trying to detect that happens once in a blue moon. If you're trying to predict something that happens once in a blue moon, you will end up basically with an imbalanced data set, because the frequency of those anomaly events are going to be much lower than frequency of normal events, right? So you have to kind of figure out, we have to obviously learn how to kind of tackle those kind of imbalanced data sets. So to do that, we had 3 techniques, right? One was change the evaluation metric at all, right? Just change the evaluation metric. The problem with just changing the evaluation metric is that even if you change the evaluation metric, it's just basically a measure of how you're tracking your model, right? So if you're using the correct metric at all to track, just changing the metric to track doesn't make the algo learn about imbalanced data set, right? So if there's an imbalanced data set, your model just would not perform good. Now you can track if it's performing good or not. You can track that very easily by choosing the correct evaluation metric, which could be AUC, which could be precision recall. That's something completely up to your choice, and you have to decide. So I've been sticking with AUC because I've been telling you that it's independent of threshold and it's class imbalance, robust to class imbalance. So given that is the scenario, you can choose some other metric as well. Now once you change the metric, you have to still make some changes, right, to make them sure that your model learns from the data. Now to do that, there are only 2 approaches. One is change the data, change the algo. Now change the data, you had again 2 only things that you could do. You could take the majority class and bring it down to the level of minority class, or you could take the minority class and bring it up to the level of majority class. So the first one was called undersampling, the second one is called oversampling. And in undersampling, we had covered multiple techniques. So in oversampling, finally we talked about changing the algorithm, change the algo, which was the second thing that we could do. In change the algo, there were 2 major things that we talked about, which is first is changing the cost function from which the algorithm learns, right? So the fourth part was basically the change the algorithm part, which is basically nothing which where we talked about two major approaches. The first one was cost sensitive training. In cost sensitive training, we basically said that okay, let's change the cost function. Say in logistic regression there's a cost function, the log loss, which we changed, and we said that if your model is basically making an error on positive classes, let's give it a lot more penalty than it's making an error on negative classes or the majority classes. So if it's making an error on minority classes, you are penalizing it a lot more. If it's making an error on majority classes, you are penalizing it less. And the second thing that we discussed was the choice of algorithm, which is basically for algorithms like random forest and decision tree. You use the same concept, right? You basically can pass a hyperparameter which is called class weight, which in turns, this intuitive idea is still the same, that if you basically pass a lot more class weightage to the majority class and less weightage to the minority class, right? So that basically you're making sure if your model is learning, you're giving enough weightage to the imbalanced class, right? So that is the algorithmic approach. And then we talked about dealing with smaller data sets, where we talked about bootstrapping, using simpler and regularized methods. And then finally, which algorithm to use. Again, please, last part of it, there's no blanket answer to it. There's never someone who's going to come up to you and say random forest always works better than decision tree, or decision tree works better than logistic regression. There's no universal truth like that. Don't try and believe that. We have already seen what are the different cases when decision tree performs better, when random forest performs better, and when logistic performs better. We have seen that some of it today during oversampling, undersampling. And let's try and keep that in mind, and let's try and build our models sequentially, starting from simple linear models and going all the way to complex models. That's the journey you should take. It's not like you should start off directly with a complex model. That's not how you do it. And that's about it. So that's all the challenges in machine learning summarized for you. Obviously, there are a lot more challenges that you would definitely face in real life. I would definitely request you guys to kind of take that time out, do practical challenges. That's how Kaggle challenges, do a lot of those practical data sets, and that's how you would get to know about the more inherent challenges of machine learning. And once you discover that, go and talk to an instructor and figure that out, how you're going to solve those kind of challenges as well. As of now, this is it. That's the end of the session for me. I'll see you on the next class. Thanks.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.